Okay, so the next topic here, standby clusters. This is another cool feature. And this is one where I think a picture is worth 1,000 words, because essentially what you see there on the right is the architecture. Actually, I have an example of this running locally in a couple Kubernetes clusters I'm going to use for the demo today. So I actually have 2 Kubernetes clusters running. I have one, which is a vanilla kube cluster, bootstrapped with kube ADM. And then I actually have an OpenShift cluster, which is going to represent my cluster on the right. And basically with this new standby cluster, and really what we've done here with this new capability is the scope of a cluster has kind of expanded beyond the boundaries, right, of a single Kubernetes cluster. So now we can have clusters across multiple, we can have Postgres clusters that span multiple Kubernetes clusters, essentially, enabling some pretty powerful architectures, right? Things like disaster recovery, where now all of a sudden you can lose your entire Kubernetes cluster, but as long as you have a standby cluster out there running in another Kubernetes cluster, you can immediately bring that one online, you can promote it, and make sure you maintain continuity of operations with your database, right? So this is really a new powerful feature because we're kind of taking some steps into federating our PostgreSQL clusters and again, expanding the scope of those clusters beyond just a single Kubernetes cluster, and that's pretty cool. So what makes this all work? Really what we're leveraging here, and as you can see in the diagram, is PG backrest and its integration with S3, right? Because S3 storage buckets are what are essentially providing this external common data store that both of our Postgres clusters running in separate Kubernetes clusters can reach into, right? So, your primary cluster that's running, say the cluster on the left there in that diagram, it can push WAL up to that S3 bucket. And from there, the standby cluster can then grab that WAL and replay it, right? And stay consistent with the changes that are being written to the primary cluster. So that S3 bucket in our current architecture is kind of the glue that pieces everything together. I do want to caveat that is the sole method that standbys work currently. There's no streaming replication or any direct point-to-point contact, between the 2 clusters. It's really via that S3, that common S3 storage bucket that they can both reach into, one pushing WAL, one grabbing it, that we're able to establish, this sort of architecture. But there's some pretty powerful things we can do with that, and disaster recovery is definitely a big one. So what I'm going to do here, again, I have some things running locally here. And for this example, I'm just going to clear my screen here. I'm actually going to be jumping between 2 separate clusters. Because like I said, I have 2 completely separate Kubernetes clusters running on my machine. So if we look over here, just to show you that real quick, if I look at the nodes I have on this cluster, you can see this one was bootstrapped using kube ADM. It's basically a vanilla 1.18.3 kube cluster. But then if I jump over here and use my OpenShift client utility and do a get nodes, you can see this is a completely separate cluster, right? And this is actually running OpenShift 3.11. So not only are these separate clusters, right, they're vastly different versions of Kubernetes, even a different product altogether. And being that S3 bucket is really all the things, your 2 PG clusters need to have in common. It really doesn't matter what Kubernetes infrastructure, your cluster is running on to make this all work. Okay, so just to look at what we have running out here real quick. So on this side, in my OpenShift cluster, that's where my standby cluster is. So before we jump back here, just wanted to show we have our standby cluster out here running in a pod. And then if I jump back to this cluster, we have another cluster called primary cluster, another Postgres cluster called primary cluster. So this one's acting as my current primary cluster, and that one over in OpenShift is the standby cluster. So only the one you're seeing here right now is able to accept writes, right? So the first thing I want to do, let's just show that data is replicating, between the primary and the standby, right? Okay, so what I'm going to do here is I'm going to log into the primary pod here and just run a quick PSQL command to populate to create a new table and just populate it with some random data. So I just created a table called my table over in my primary cluster and just inserted some random data into it. Okay, so now I'm going to expect that to replicate over to my standby. Now, again, like I said, there's no streaming replication or anything like that. So we do have to account for a bit of a delay here. S3 adds to that a little bit, in addition just to the fact that we got to wait for Postgres to loop around and grab that wall and replay it, right? So I'm going to log into the standby cluster here in a second and show that that data does exist. But while we wait for those pieces to fall in place, just wanted to talk some semantics of standby clusters real quick. And what you're going to find when you're creating standby clusters is, in a lot of ways, they work like just any old Postgres cluster in the operator. The same leader election semantics apply. So you still have leaders and followers in that sense. You can do things like adding and removing replicas. So you can scale up and scale down your cluster, just like you always would. So a lot of the same PGO commands you're used to working with do work as expected. So for instance, if I want to scale, let's just do that real quick. I'm going to scale up the cluster. And we can see now we have a new container that's being created here, which is essentially going to bootstrap as a replica following the standby cluster leader, which itself is replicating from that other primary cluster. So lots of levels of replication occurring here. But there are certain things we don't expect to be able to do in a standby, right? Because really the primary database should be running the show, right? So we don't want our standbys doing things like backups or restores, right? Those things should all be managed by the primary cluster. So what you're going to find, just to show a couple examples here, if you try to do something like create a backup, for instance, that request is going to get rejected by our API server. And it's going to say, hey, you can't do this because you're in standby mode. Same with a restore, right? The request gets rejected, because you just shouldn't be doing those things from a standby. Okay, so let's just jump into our standby here real quick and just see if our data has replicated. Oops, looks like I have a wrong pod name there, so just bear with me for 1 sec. There we go. And that table I had created was called my table, and boom. Okay, our data has replicated over to the standby. Okay, so let's have a little more fun here. And just to show that this really is a standby, if I were to try to create some data here, you'll see we get our typical, in a read-only transaction state, which is what we would expect, in a standby cluster, right? Because it's replicating from the primary. So let's demonstrate essentially a failover scenario and just how that would work real quick. So of course, so let's say, that going back to the diagram we looked at, let's say something, there's some disaster that forces us to shut down the Kubernetes cluster where our primary is running. So now we want to bring, promote that standby cluster, make it the new primary. So what we're going to do, of course, we want to do this in a controlled manner, right? So the first thing we're going to want to do is shut down our existing primary. The one thing we don't want is there to be multiple primaries out there, right? Trying to write to that same S3 storage bucket, trying to push wall and things like that. So we do need to do this gracefully. So the first thing we're going to do is shut down our primary cluster. And our PGO update command now has a shutdown flag that facilitates that process. So what I'm going to go ahead and do is issue that command. What we're going to see here once I do that is our pods are going to start terminating. And really all we're doing behind the scenes are scaling all the deployments that are out there for the cluster down to 0. So things aren't getting deleted. We're just scaling things down and shutting them off. And obviously, this could be beneficial outside of this specific use case, right? If you just want to shut down your workloads at the end of the day or whatever it might be, you can now gracefully scale everything down. Okay, so at this point, we can see there's no pods left, right? We have a couple completed jobs floating out there, but there's nothing actually running. So our primary has been shut down. So now we want to promote our standby cluster. So I'm going to jump back over here. And it looks like I need to get out of here. And I'm going to issue another update command against our standby cluster, this time with a promote standby flag. And what that's going to do where we're actually look at some of the logs here of that pod, you can see for a while here, this cluster was happily running just as the standby leader. But as of that change now, we can see, there was a little activity that occurred here, but now it is the actual leader. So what we've essentially done is promoted that standby to become the new primary. Okay, so final step here. Now we want to turn our original primary into a standby. That's also possible. So to come full circle here, I'm going to jump back over into this cluster. Our cluster is currently shut down, right? Because we had shut it down. What I'm going to do is now update it with this enable standby flag. Basically, what that's going to do behind the scenes is destroy any PVCs, because what we're going to want to do is re-bootstrap from the new primary. So we've enabled standby. Our PVCs have been recreated. And now really all we have to do is start the cluster back up. And now there's a startup flag that you can use to do that. So we start the cluster back up. And what we'll see here is that our pods are going to start creating. I'm not going to wait for this to actually bootstrap because thanks to S3 and a little latency, it does take some time. But that's effectively what's occurring here. Now the old primary is going to re-bootstrap from the new primary cluster, and it's going to become the standby cluster that follows that other primary. So cool. Well, I think that basically sums up the demonstration here for standby clusters. So I'm just going to jump, moving real quickly here into our last topic, which are namespace modes. Okay, so namespace modes. These are really a new concept that was introduced in the 4.3 release, really as a result of a lot of feedback we've received. I'm really going back to version 4.0 of the operator. And if everybody remembers, version 4.0 is essentially where there were some big architectural changes made to the operator, where it went from being able to support just a single namespace to being able to support multiple namespaces. And along with that capability came a lot of great new functionality within the operator as well. All of a sudden, the operator itself could do things like create new namespaces. And it could also do things like reach into those namespaces and create resources like service accounts, roles, and role bindings. So it could essentially assign itself the privileges it needed to create PG clusters in various namespaces. So it could do all these powerful things all of a sudden. Now, of course, despite that functionality being great, there is a downside to that, right? Because with all that great new capability came a lot of new permission requirements. All of a sudden, the operator account, the account that's running the operator needed a lot more permissions to be able to do all these great things. And a lot of those permissions came in the form of what we call cluster roles in Kubernetes terms. And really what those are roles. They're not scoped to a specific project or namespace. These are roles that are and permissions that are applied cluster-wide. So when you're assigning these sorts of roles, it can often be a pretty big deal because you're giving an account a pretty wide swath of permissions to do things across the entire cluster. And a lot of the direct feedback we've received was that in certain environments, certain environments that are very secure or very highly governed, these cluster roles can often be problematic, right? So what we realized we really needed to do was provide a greater degree of flexibility when you're installing the operator to reduce or perhaps even eliminate the need for those cluster roles altogether, and make sure we're meeting the security requirements of any of our users, customers, et cetera. And that's really where these namespace modes came from. Now, there's always going to be a trade-off, right? When we start pulling permissions away from the operator, it's not going to be able to do as much, right? When we give more permissions, it can do more. So there's always going to be a trade-off here in terms of, you start pulling some privileges away, we might have to disable or limit certain capabilities in the operator. But what was important to us at the end of the day was to give you the options to make those decisions around those trade-offs yourselves. So you could balance security and functionality based on the specific needs of the environment you're working in. Okay, so with these namespace modes, there's really 3 of them, and that's what you're seeing on the slide here. There's one called dynamic, another called read-only, and finally we have one called disabled. And with each of those different namespace modes, there are different cluster role requirements. Dynamic requiring the most cluster roles, as you can see here, read-only requiring a small subset of them, and then disabled getting rid of those cluster role permissions altogether. So what does that really look like here? So for this example, I'm not going to show any PG clusters or anything like that. Really, I just want to explore my local install a little bit. Because right now, the install I have running is running in a dynamic mode. Well, how do we know that, right? Well, going back to what we just saw on the slide, cluster roles are really the deciding factor, right? So if I look out in my current environment, I can see that there's a cluster role called PGO cluster role. And that cluster role has been bound to the Postgres operator service account. So I can see that my current operator install is essentially assigned all these permissions, which basically enable those dynamic namespace capabilities. And you can see it allows the operator to do a lot, right? Across the entire cluster, it can create, update, delete namespaces. It can create roles, service accounts. So basically it can create permissions and assign those permissions to things. It can do quite a bit. Well, what does that mean in the context of the operator? Well, that means you can do things like create a namespace directly from the operator using like the PGO client utility. And not only can the operator create that namespace itself, but if we go look inside of that namespace, we can see that the operator created all sorts of stuff within it when we issued that command. It created service accounts it needed. It created roles it needed. And then it bound those roles to its own service account. So basically it signed itself the privileges it needed to work within that namespace. And of course we can do things then like delete that namespace all directly from the operator. And then there's also some things that are occurring behind the scenes as well. Basically with the privileges we have here, specifically some of these get list watch privileges for namespaces, the operator can actually detect when namespaces come and go. So that means some of the things we run behind the scenes, things like controllers that listen for events in certain namespaces so the operator can react accordingly, we can automatically detect that namespace was created and we can start wiring those things up. And then when the namespace is deleted, we can start tearing them down. So while in this mode, the operator can really dynamically respond to the world around it. Okay, so let's look at basically the polar opposite at this point. What I'm going to do is reinstall my operator here in a disabled mode. And I'm using bash install here just for the purposes of the demo today. But you can see I flipped this bash install variable to disabled. And I'm going to reinstall my operator here. This will just take a second. Okay, so the first thing we're going to look at once this comes back online are our cluster roles, right? Because that's always the differentiating factor between these modes. So we can see this time when I tried to look for that PGO cluster role and the cluster role binding, it doesn't exist, right? So now if I try to do something like create a namespace, my API server's not up yet, so sorry about that. Okay. So when I try to create a namespace, you can see that now it spits back an error, basically telling me that operation is not allowed in the current operator install. And what's really happened behind the scenes here is the operator has detected, I don't have the create namespace privilege, and it's adjusted its behavior accordingly to not even attempt to create it. So it's not even going to try to do things it knows it can't do. So that kind of shows you how these modes have now been baked into the operator, and it can dynamically adjust its behavior based on the permissions it sees. So what if you do need to add a namespace while you're in this mode? And I'm just going to touch on this real quick because I think I'm running out of time here. But basically, when you're in a disabled mode, that means, when we created that namespace in the dynamic mode before, right, the operator created the namespace and all those resources in it, service accounts, roles, role bindings. Well, when we're in a disabled mode, that means we have to do those things manually. Some administrator is going to have to go create those things for us. Now, of course, we have some helper scripts out there to assist in that. We have this add targeted namespace script in our repo that facilitates that process. So I'm just going to go run that real quick. And that basically equates to someone manually creating all these various resources within that namespace. However, what you'll notice, if I go try to create a new PG cluster in that namespace, the operator is going to complain. Well, that's because we're in this disabled mode, right? So the operator had no visibility into the creation of that namespace. It had no privileges to be able to see that. So what that means when you're in a mode like this, you're actually going to have to go back and redeploy the operator, either via one of our installers or just directly updating the deployment to point to that new namespace. And then when it restarts, it'll pick that up and move forward. So hopefully that kind of highlights some of the differences here between these different modes, and you can kind of see kind of the polar opposites between that dynamic and disabled mode, as to what the operator can automatically do in one mode, and then how some manual steps are required in the other mode. The one I didn't have a chance to touch on today is read only, and that kind of fits in a sweet spot in between. So hopefully there'll be a chance to talk about that at some point when we have some additional time. But at least just wanted to give you an overview of how some of these namespace modes work. So at least you have an idea of what we're talking about when these topics come up.